Hello everyone, I'm Joe. Uh, Today we are going to start talking about the other big category of logic circuit, which is sequential logic. And let's first look at some basic devices used in sequential logic. If you remember these slides before, I showed you the difference between combinational logic and sequential logic. Uh, so up till now, everything we learned before belong to combinational logic. Basically, the output of our logic circuit is has a direct relation with the input. However, in sequential circuit, the output value does not only depend on the present combination of the input, but also it's a function of its previous states at the output. Okay, and today we are going to learn the two basic elements that form any kind of sequential circuit. They are the latches and flip-flops. Later on, we will look at the modular sequential circuit, counters and registers. To help you understand why the output of the circuit could be a function of its previous status, I use this elevator example. For instance, there is a 6th-floor building and they got elevators. Say you are on the 3rd floor and want to go up to the 6th floor. So basically what we do is to press the up button on the elevator and wait for it, right? However, depending on where the elevator was or is, okay, the elevator may have different movement. Let's see. In case A, say the elevator is on the 1st floor. So how will it operate? So if we use a table, our input is still is the up button, right? Currently, the elevator is idle. It's idle, but it's on the 1st floor. Then how will it move? Everybody will move up, right? So the output here is the movement of your elevator. It moves up. However, if the elevator is on the 4th floor right now, say you're still going to press button. You want to press down, right? Because you want to go up. The elevator is on the 4th floor, so the current state is 4th. Then how will it move? It will move down. The third case, if the elevator is on the 5th floor, but someone on the 6th floor pressed down button before you did press the up button, how will it operate? Here our input is still up button. Right now the elevator is 5th floor. However, because somebody pressed the down button before you on the 6th floor, so actually the elevator will go up first, right? So you see, we have same input, but depending on the elevator's present state, its movement may be different. So that's the idea about sequential circuit. So you must know the present state, or sometimes we can say the previous state. Then you can figure out the output for now or for the near future. Okay, so that's the property of sequential circuit. Okay, so this is a block diagram of a typical sequential system. Okay, sometimes we also call them like state machines. So in this machine, we have two parts. The first part is the combinational logic circuit. So this is just what we learned before, like using logic gates or modular circuit to build up a circuit where the output is a direct function of input. Okay, but it has a second part, which is the memory device, where it stores the present or previous states of your circuit. Okay. And we have some special devices that can be used as memory device. Okay, let's look at the first memory device, which we call it latches. Okay, and more specifically, we call it set and reset latch. This is the most basic device that can be used to store information, one bit of information. So here is a logic diagram of the latch, and this is a symbol. Okay, basically a latch can be formed if we collect the output of the first NOR gate to the input of the second NOR gate, and the output of the second NOR gate is collected to the input of the first NOR gate. So we use some feedback loop for two NOR gate. We can form a latch. Let's check how it works. So on the right, I have the truth table for this latch here, and because this is sequential circuit, so we must know the current state of the output so we can predict its next state. Remember the animator example, right? So here Qn, basically n stands for present state, okay, and Qn plus 1 stands for the next state, like what will happen to the output at the next moment. All right, so let's check the first combination. So 0 0 0, which input is 0 0, and the present state is 0, so which means Q equal to 0, and the Q bar should be 1 because Q bar is always the opposite of Q. Okay, so let's check this circuit with those values, see what's going to happen. Because the output is 0 here, so this 0 will pass to the input of the second NOR gate, and 0 0 we are supposed to get a 1 here, right? And so we get 1 here, 0 1 we're supposed to get a 0 and output for this one. So basically everything is kind of balanced, it's stable, so nothing got changed in this case, which means at the next moment Q still equal to its present value. So Qn plus 1 equal to Qn equal to 0. Okay, then 0 0 1. So R is 1. R basically we call it reset input. So let's see how it's reset here. So if R equal to 1, we still, and the current state is 0. So we still have the 0 and the 1 and these two nice. Then 1 1 for the first NOR gate, we're supposed to get a 0. It's still okay. And 0 0, we're supposed to get a 1 here. So everything's still in balance, nothing gotta change. Alright, so next one, 0 1 0. So for next, we got S equal to 1, R equal to 0. And S is called set input. So let's see. In this case, for the upper NOR gate, we got 0 1. The output should be 0. And for the lower NOR gate, we have the input at 0 1. So the output should be 0. Okay, so if we call this is the case t equal to 0, the starting point. This is apparently it's not in balance, right? Because we're supposed to get a 0, but it's not. So basically, after a short amount of time, say t equal to t1, the Q bar should become 0, which will also update this input to 0. Then we will see that the first NOR gate is not stable anymore because 0 0 requires a 1 as output. So basically, after t2, when t equal to t2, then this will be Q will be updated to 1, and the 1 1 we still get 0 here. So Q bar will not change. So actually the final state will become to 1 0 for the output. So which means qn plus 1 equal to 1 in this case. And when qn plus equal to 1, we say it gets set. So this is the set input. It's active high signal to set the output. Okay, so we can call this set. Actually, for this one, we can call it reset. However, for both are 0, we call it stable or no change state. Okay, let's keep going. So 0, 1, 1. Let's see what will happen. Let me wipe this. So still t equal to 0. Output is still 0, 1 initially, but we have 1, 1 as input. So we have 1. So we have 0 here and 1 here. So 1, 1 still ask for 0. So this will not change. 1, 0 ask 0 here. So at t equal to t1, this will become 0, 0. Okay. Then we have 0, 1. It asks for a 0. 0, 1 asks for 0. So you see the issue. Actually, in this case, if I have both s and r equal to 1 at the same time, the output q and q bar will be forced to be 0 at the same time. But because q and the q bar is always the opposite of each other, actually this is not a stable state. We got a problem here. Actually, if we change rs back to 0, 0, okay, so say let's still got 2, 0 here. So what will happen, because both inputs for the two NOR gate are zeros, they are required a 1. So both output will change to 1. And at the next, and after a certain time, because these two lines are 1, then the NOR gate output will be asked to change to 0 again. So basically we are getting a oscillator. So the output is oscillating between 0 and 1. So you will, the output q or q bar, they got same value always, and they keep oscillating by itself. It's not a stable state. So if we want to store information, we don't want to use this state. Okay, basically we don't know because what's the output? It's keep changing. So do not use this. Okay, or forbidden in some book. It's called forbidden state. Okay. Then let's check 1, 0, 0. So this is 1, 0. We got 0, 0. So we have 1 here. We have 0 here. So 0, 0 asks for a 1. 1, 0 asks for 0. So everything is in stable state. Nothing gonna change because the output, initial output is 1. So next still be 1 because it's not changing. Okay. So there's still no change. Then 1, 0, 1. So R is 1 this time. If you remember, R is called reset input. So we're supposed to reset the whole thing. So let's see, because now for the first NOR gate we got 1, 0. It actually required 0 as output. So after a certain amount of time, we will see this equal to 1, to 0. Okay, and we got a 0 here. Now 0, 0 requires a 1 here. So at T2 we will have 1 here. Now everything is in balance. so it will stay there. So you can see we had the output change from 1 to 0. It's being reset, so we call it reset. And the 1, 1, 0, this is 1, this is 0. So in this case, actually, we can do similar analysis, but you will find the next state is being set. Okay, even though it's already 1, but it's still equal to 1. This does not mean it's not changing. It means it's being set because the set input is active. Here, the reset input is active, so the output is 0. Okay, and the last one is still. We can do similar analysis. You will find the output is still kind of vibrating, so it's no use. Okay, this is set. So you can see that we can summarize this the behavior of this latch into 4 different states: no change, reset, set, and no use. So basically, when SR is 0, 0, it's no change. Whatever your previous state is, it will keep that value. Okay, 0, 0, 1, 1, right? And if R equal to 1, like this 2 here, okay, it always reset the output. It doesn't matter what's your previous state, the next state will be 0. Okay, we call it reset. If S equal to 1, it will set the output to 1. Okay, and lastly, if SR equal to 1, 1, don't use the latch in this state. Try to avoid that. Okay, we spend a lot of time to show you how we can do analysis of the basic latch to figure out its truth table. But actually, you can tell after we figure out everything, we can summarize the behavior of SR latch into very simple tables. So let me redo previous slide for you in a simpler way. So for the SR latch, SR there's no bar on it, which means both SR are active high. Okay, so what will happen is we have SR, and we must know Qn to figure out Qn plus 1. Okay, so 0, 0, you know that means no change. No change means it doesn't matter what happened to Qn. Qn plus 1, just follow Qn, right? 0, 1, this is called reset. So it doesn't matter what happened to current Qn, the next state always equal to 0. 1, 0, S is 1, which means it's a set state. So it's always set the next state to be 1. 1, 1. We don't use, so no use it because you don't know what's the output. It's keep changing. Simple enough, right? Now, the second type of latch, which is called S bar R bar latch. This is because you see the name has a bar in it. You know S now. It's just different version of SR with active no control or input here. Okay, so in the S bar R bar latch, we use NAND gate instead of NOR gate, but we can do similar analysis. Basically, it still has 4 states, but it's opposite. Okay, when 0, 0, when S bar and R bar equal to 0, actually this is the no use or forbidden state. So we'll try to avoid that. Okay, 0, 1, because we don't have to do the analysis because we saw the name is active no now. So 0 means S is active. So S means set. So you can immediately figure out it will set the output to be 1. 1, 0, R bar is active. So it's a reset. The output will be 0. 1, 1. Now this is corresponding to the no change. So no change means follow the current state, which is 0 in this case. 1 0 0 don't use. Okay, it's oscillating. 0 1 set. 1 0 reset. 1 1 no change. Just follow what you have. We can also write this in a shorter way. So we have S bar, R bar, Qn plus 1. Actually, we don't even need that. So 0 0 don't use. Okay, 0 1 set, 1 0 reset, 1 1 no change. Just follow whatever you get from current state. In many cases, we also need to add an enable input for the latches. Then it's called gated latches. Here is one example for the basic gated SR latch. So what we do is we have the S bar R bar latch, if you recall the circuit, and add another level of NAND gate with the input SR and E is the enable. So if E equal to 0, the output for both NAND gate will be fixed to 1, right? And the 1 1 for this S bar R bar latch, that's corresponding to no change, right? So which means Qn plus always equal to Qn, so nothing gonna change. So in this case, it's a little bit different than the enable case when we're talking about the modular combinational circuit. So when E equal to 0, it simply means the output don't change. Okay. And if E equal to 1, the output of these two NAND gate is the opposite of the input. So if S equal to 0, this will be 1. If S equal to 1, this will be 0. Okay, so now let's look at this case. So SR equal to 0 0, which means we get a 1 1 here. 1 1 is no change for this S bar R bar latch, right? It's still no change. 0 1, so we got 1 0 here. For this latch, let's say reset state. So basically, because of the NAND gate, the active level for this S bar R bar latch is reversed. Now it's active high again for the whole thing. So R equal to 1 means reset. So you will get 0. 1 0, that's set, you will get 1. 1 1, that's forbidden or no use. So don't use this. Okay. So that's how you handle the gated latch, and that's a symbol for that. If we collect the S input and R input of the gated SR latch together using a LOT gate here, we get a gated delay latch or D latch. For D latch, we only have 3 states. The first one, if E equal to 0, here E basically is this C here. Okay. So this is the active high enable input. So if it's 0, then we know this latch will be no change. So Qn plus 1 equal to Qn. However, if E equal to 1 and D equal to 0, so basically means S equal to 0, R equal to 1. We know this is the reset state. So Qn plus 1 equal to 0. And this is a reset. And if D equal to 1, E equal to 1, okay, so we got 1 0, and that's set, right? But if you compare the D value and the Qn plus 1, you will find the Qn plus 1 always follow D when the enable is active. So that's why it's called D latch. Okay. Before I think we can do a two column map here, but we don't have to do that. It's very easy to remember. You don't need the Boolean expression actually. Okay, if you understand the operation of the SR latch, S bar, R bar latch, and D latch, that's pretty much everything for latches. Even if there are some other type of latches, I believe we can understand them too if you know these three basic ones. But one important thing, one important practice of using the latches is that to figure out the timing diagram of the output of a latch. Basically, you just need to remember those 4 states for the latches. But in most of the case, just 3 states because we have the no use states, right? For D latch, we don't have that, but for SR and S bar latch, we have a forbidden state. So you won't actually see that in the real problem. So let's try to solve 2 examples here. Say we have a S bar R bar latch, and the S bar R bar input follows this pattern. The waveform follows this pattern as a function of time. So what's the waveform for Q and Q bar then? We just need to figure out Q. Basically, this means Qn plus 1. So we try to figure out the next state. And when we talk about the latches and later on the flip-flops, basically all the memory devices, we have to specify the current state because we already learned that, right? The next state is kind of related to its current state. So we must specify that. So here is specify that Q is initially no. So basically, based on that, we try to figure out Qn plus 1. All right, let's start from here. So first we see that S bar equal to 0, R bar equal to 1, right? What states is that? S is active, so it means set. And the Q is initial no, so it go set first, which is 1. Then until here. Here we have 1, 1 for S bar and R bar. What's that? That's no change, which means it will, because when we're talking about this part, the previous part become current state. This small part is the next state. So we will use this value as present state. Present state is 1 and there's no change, so it will keep to be 1 until this location here. Maybe a different color. Okay, then after that we have 1, 0. So now R bar is active, which means reset. So it becomes 0 here, and follow that until here. Then we have 1, 1. So again, that's no change, right? Then we have 0, 1, and 1, 1. So again, we have set, then no change, which means we need to set the output, then keep it until this point. Then we have 1, 0. Now it's reset again. So reset, and we have 1, 1. So no change. Then we have 1, 0. So it's still reset. So just keep going. And 1, 1. No change. Then we have 0, 1, which is set. So change to 1 here. And we have 1, 1. So no change. And 0, 1, which is set. 1, 1. So that's how the Qn plus 1 look like, okay, for the given input. Similarly, we can try with this D latch. And this D latch has the enable input. So let's just put EN here. Okay. Similar way, but we have to now use the choose table for D latch. Say because initially enable is not active, right? When enable is not active, the Qn plus 1 just follow Qn. And let's see, Qn is initially reset, so 0. So it will follow 0 until the enable is active. When enable active, if you recall that the output will what? Follow D. So Qn plus 1 just follow D here. So D is 1, it's 1 here. Okay, and at this moment, the enable become inactive again. So it won't change. And until next enable signal coming, nothing gonna change. Okay, and then at here we have 0 for D, so output will follow D to be 0. And after this, enable is not active, so it will keep to be 0 until next enable signal coming. Okay, and now it become to 1 again. And from here to here, the enable is always inactive, so which means the output will not change at all until this part, until here. After this point, the enable input is always active. Then what will happen? Qn plus 1 will simply follow D. So in order to figure out this waveform, you must be very, very familiar with the operation of the latches. Okay, finally, just to show you some like commercialized product in the 74 series. Okay, you probably won't see this much in the market, but in old time they are pretty popular, like in the labs. Okay, so this 279 is a quad SR latch module, so it has 4 kind of individual latch modules there, and the other 175 is a quad D latch modules.